Hello and welcome to our lesson on polar equations and graphs for our trigonometry class. This is going to be section 9.2, and we're going to talk about all things polar, basically graph related, okay? So what I have in front of you here is the chart showing all four types of polar graphs that I'm going to need you to know. And those four types are cardioid, Limacon, Lemniscate, and rose are the four types. And so let's go through the chart and make sure that we've covered all of the cases. Starting with cardioid, you're going to notice that here they give us the standard form, which is r equals a plus or minus a cosine theta, or r equals a plus or minus a sine theta. So if you look at the shape that it gives us here, I don't know what you might call that, an apple with the stem at the origin, maybe, I don't know. But the thing you need to notice here is that the constant and the coefficient of the trig function are identical to create a cardioid here. So for an example, it might say r equals 2 plus 2 cosine theta, and you know that's going to produce a cardioid. Now, Limacon without an inner loop is going to be r equals a plus or minus b cosine theta, or it could be r equals a plus or minus b sine theta, where the constant has to be greater than the coefficient of the trig function. So an example here might be r equals 4 minus 2 cosine theta, and that would produce this, well, it looks like an apple shape where the core is the origin. Instead of where the stem is, here it's the apple core at the origin. That is a Limacon without an inner loop. Then you have a Limacon with an inner loop. And in this case, it's the same formulas, the same basic formulas as the previous. However, the coefficient of the trig function will be greater than the constant in this case. So an example might be r equals 2 plus 4 cosine theta, where the coefficient, the number attached to the trig function, has to be bigger than the other number. All right, moving on to the lemniscate. Notice that a lemniscate makes a figure 8. And that's the way I remember that. Lemniscate, figure 8. Those formulas would be r squared equals a squared cosine of 2 theta, or it could be r squared equals a squared sine of 2 theta. Notice that the angle has to be a double angle, and the r and the a have to be squared. And that will produce your figure 8, which is a lemniscate. And then the last shape is a rose, which is r equals a sine of 3 theta, or it could be r equals a sine of 2 theta. The coefficient of the angle is going to tell you how many petals your rose has. So listen to this. If the coefficient of theta is odd, like in this case, the rose with 3 petals, if the coefficient of theta is odd, that coefficient is the number of petals. So if you have r equals 5 cosine of 3 theta, the 3 theta is going to say 3 petals. If it was 5 theta, then you would have 5 petals. If the coefficient of theta is even, then the number of petals is that even number doubled. So in this case, we might have r equals 5 cosine of 2 theta, and when that coefficient of theta is even, you have to double it to get the number of petals. So if this would have been 4 theta, then you would have 8 petals. Odd coefficient of theta, that's the number of petals. Even coefficient of theta, double it to get the number of petals. And that is way too much talking, okay? But that's me talking through every possible shape. And then the next thing we're going to do is we're going to look at how would we graph this manually, and then we're going to look at how would we use technology to help, okay? So I have an example. Here we're going to graph the equation r equals 2 minus 4 cosine theta. Now in this case, this would be a and b. We can see that the coefficient of the trig function is bigger than a. And remember, in that case, when that happens, that's going to be your Limacon with an inner loop. When b is greater than a, that's a Limacon with an inner loop. So we know kind of the shape to expect, but if you're going to graph this manually, what you're going to have to do is make a table of values. I've used all of the important angles in the unit circle, starting at 0 and going all the way to 360. And what we're going to do is we're going to generate some points using the calculator. So we're going to type in our equation, which is 2 minus 4 cosine, and then we're going to start with 0. I am in degree mode, and that's going to give -2. Now, you can see we're going to have a lot of ordered pairs. So just hang loose. We're going to do this a few times, okay? It's not going to be too bad since I can delete and repeat. And I'm going to have to hit my SD button to get a decimal approximation. -1.5, let's call it. -1.5. We can approximate. In this case, that's going to be good enough. And next is going to be 45. Approximate -0.8. And we're just going to rinse and repeat. Delete, let's see, backspace. Next is 60. Can you tell that this is labor intensive? This process, that's why I'm only going to do this one time. This is way labor intensive, but this is what you do if you want to show work. 90 is 2. Delete, delete. 120. 4. 135. Whoops. Approximate. 4.8. 150. 5.5 approximately. 180. 6. Now, let me slide this over so my calculator won't be in the way. 210. 5.5. 225. 4.8. Can you see we're going back down now? I'm seeing some symmetry now. 4.8. So I bet the next one is 4 and then 2 and then 0. Is what I bet. Let's see. 4 and then 2 and then 0. There's 4. 2. and 0. Okay, like I predicted. So here we go. 4, 2, and 0. And do you think that's going to keep repeating and go negative 0.8, negative 1.5? We're going to see. Oh, there you go. Symmetry. We got symmetry. Negative 0.8. I bet negative 1.5. And then negative 2 is what I predict. Let's make darn sure. 330. SD. There's the negative 1.5. And 360. Whoops. Negative 2. Okay, so there is all the manual labor done. Now what we have to do is we have to go through and plot these points. All right, so let's be very careful here. And at 0, we're going to be at negative 2. Now, if you remember in the previous lesson, we talked about how do we plot polar points. Well, if the radius is negative, you have to go in the opposite direction. So negative 2 is going to be right there. In the direction of 0, we're actually going to go the opposite direction 2 units. And then in the opposite direction of 30, we're going to go 1.5. In the opposite direction of 30, that's going to be right there. In the opposite direction of 45, that's going to be 0.8. That's going to be right here. 60 is 0. We're going to be at the origin. 90 is 2. Now that's going to jump up to here. Since the radius is positive, we are going to go 2 units in the direction of 90. In the direction of 180, we're going to go 4. I'm not 180, 120. 1, 2, 3, 4. We're going to be at 4. And then at 4.8. And then at 5.5. And then at 6. And if you're following those circles, I'm trying to make sure that I'm staying on track. So there's the first half. And if I play connect the dots, you can see that we've got this kind of spiral shape going on like that if I play connect the dots. Now let's keep going. At 210, we're at 5.5. Next, we're at 4.8. And then at 4. And then 270 is back at 2. And then 300 is back at 0. So if we keep going here, and you can actually see the direction that this graph starts. It starts here at our first point, and it curves around and then back into the origin. And then at 315, I'm sorry, at 300, we're at 0. At 315, we're at negative 0.8, negative 1 point, whoops, I put that in the wrong spot. Negative 0.8, negative 1.5. So that's going to complete this inner loop part here. And as you can see, we did get a Limacon with an inner loop as predicted. Whew, man, lots of work. Let me introduce you to DESMOS, okay? This is how I'm going to recommend that you play with and explore these polar graphs. So what I've got here in DESMOS is I typed in my equation, and if I turn that on, you're going to see exactly what we drew, okay? So I'm going to minimize that, and you'll see that what we did manually, we can verify electronically with DESMOS, okay? Now, one of the cool things about using DESMOS is you can change things on the fly to see how it affects the graph. Like if you were thinking, well, how different would this graph look if it was sine instead of cosine? You can easily come in and delete your cosine and type in sine, and you can say, oh, well, that's how it would change the orientation. It wouldn't change the size or the shape, but it changes the location of your limacon with an inner loop. Or you can say, well, what would happen if that 2 was a 4? And then you get a cardioid. Remember, the cardioid has this apple shape with the stem at the origin. And then you can say, well, what if that was bigger? And then you get your, that's not quite this, well, it's similar to an apple shape, but here the origin is not where the stem is. It's more inside the apple. Anyway, you can see how that changes the shape of the graph. Now, what I'd like to do is explore a few more graphs just to give you an idea, okay? So let's type in R equals 3 cosine of 2 theta. Now you are going to have to use theta, and the way you get theta is from the keyboard with the ABC button, and then all the way over here is theta. Okay, so if I minimize that and hit enter, you can see that we do get a rose with 4 petals as predicted. Remember I said in this layout, let me go back to here to the formulas. Remember I said for the roses, it's going to have this shape here or this formula. And so what we have is R equals 3 cosine of 2 theta, which is this formula right here, where A is 3. And I said if the coefficient of theta is even, you have to double it to get the number of petals. So there's that one. And you can, like I said, you can play with this and say, okay, what if the 2 was a 3? Well, remember I said if it's an odd number, that's the number of petals. And so if it was a 3, you'd get 3 petals. Or 5, you get 5 petals. Okay, and then you can change the cosine to a sine, and you're going to see that it changes the orientation. And I think you're going to notice that the coefficient is the length of a petal. So the 3 in this formula is from the center to the edge of the petal, it's the length of the petal. And you can change that and say, well, what if that was a 5? And now you can see that the petals go out 5 units. Or if you change that 5 to a 7, and you get 7 leaves, okay? Now let's see if I was right. What if that's an even number like 4? Well, you should get twice as many petals. 1, 2, 3, 4, 5, 6, 7, 8. So you get 8 petals, and the 5 is still the length of the petals. So there's the petals explored, the roses. Let's look at this one. How about R squared equals 9 cosine 2 theta. And remember for theta, it's the keyboard, the ABC. Bam. Enter. Whoops. It didn't like that for some reason. R squared equals 9 cosine of 2 theta. That should have produced a lemniscate. And so why does it not like, I bet it doesn't like the squared. Well, to get rid of a squared, you have to take the square root of both sides. So what if I square root that? There we go. Square root of 9 cosine of 2 theta. Aha. So it didn't like the R squared, but if I take the square root of both sides, I'm going to get my lemniscate. And then if I copy and paste that, copy and paste, and change the cosine to a sine, You can see the difference there in orientation. Okay, so the cosine is going to make a figure 8 horizontal, and the sine is going to make the figure 8 at a 45-degree angle there. So there's the difference in the two lemniscates. And I believe there's only a couple of other things that I wanted to look at in this section, and then I'm going to call it good. Okay, so exploring the graphs, I would highly recommend that you use DESMOS to play around with that and explore and get familiar with those. The other thing they're going to ask you to do is convert. We're going to be given equations and asked to convert them. So let's start with r equals 4, and it says transform each polar equation to a rectangular equation. So this is similar to what we did in the previous lesson, which means you're going to need to remember those formulas we covered. One of those formulas was r equals square root of x squared plus y squared. And so here, if I want to convert this to a rectangular equation, I can replace r with what it's equal to. And that's going to give me the square root of x squared plus y squared equals 4. And then if I wanted to simplify that by getting rid of the square root, I could take and square both sides, which will give me x squared plus y squared equals 16. Now this is rectangular. This up here was polar. And let's talk about what the graph would be. So if you look at your polar equation, it says r equals 4. What that basically is telling you, it says, hey, you've got a radius of 4, and the angle, since theta is not mentioned, theta can be whatever you want. But the radius is fixed at 4. So no matter what angle you're at 0, 90, 180, 270, you're always going to be a distance of 4 units from the origin, and that represents a circle. Guess what? So is this. X squared plus y squared equals 16. That fits the standard form of the equation of a circle, which is x minus h squared plus y minus k squared equals r squared, where your h and k would represent the center of the circle, and here h and k would be 0 to give us just x squared and y squared. So that says the center would be at the origin, and the radius squared, we know that 4 squared is 16, so the radius here would be 4, which is what the polar equation said. And so what do you need to take away from this? You need to know how to convert polar to rectangular, but it's also nice to have an idea of what the graph is. Okay, let's do one more of those. Let's say that they give us theta is pi over 3, and they want us to convert to rectangular form. So we know that this is polar form because we've got r's or thetas, well, specifically theta this time. Notice this time theta is fixed, but the radius is not mentioned. There's no r in this formula. And so the radius can be anything, but the angle is fixed at pi over 3. Now, what does that mean graphically? Well, where is pi over 3? Pi over 3 is in the first quadrant. But if the radius can be anything, that means the radius can be positive or negative. And so in this case, that would represent a line. This is a linear graph that goes through the origin, and has a slope of, greater than 1. I'm not exactly sure what the slope is. Hey, but guess what? We're going to figure that out in just a second when we convert to rectangular form. So here's the formula you're going to need to remember. Theta is the inverse tangent of y over x. And so here I can replace theta with the inverse tangent of y over x equals pi over 3. And then I can manipulate this equation into slope-intercept form. Watch the magic happen. Here we go. Bringing the inverse tangent over is going to turn that into regular tangent. And we know that tangent of pi over 3 is a value. So let's calculate the value of tangent of pi over 3. And since I don't want to switch to radian mode, pi over 3 is equivalent to 60 degrees. And that's going to be square root of 3, which is approximately 1.7. And I'm going to use the approximate value just for fun, just to illustrate the example here. So we've got y over x. This value is about 1.7. And then if I multiply both sides by x, that's now going to be slope-intercept form. Y equals 1.7x, which if I write down the slope-intercept form below that, we can see that our slope is 1.7, which I said was a little bit greater than 1. And our y-intercept is 0 because there is no number there. So that means we have a line that goes through the origin. The y-intercept is the origin. And if I do rise and run, that's going to be up 1.7 and over 1. From the origin, I can rise 1.7 and run 1, and I get my line. So again, the takeaway is you need to be able to convert from polar to rectangular, and you need to have an idea of what does that graph look like. And so there's two examples of going from polar to rectangular. And I think that's going to wrap it up for this particular lesson, okay? So if you have any questions or comments about anything we've covered in section 9.2, please feel free to leave a comment in the comment section below, or you can text me. And thanks for watching.